Good afternoon, everyone. Welcome to this webinar on the integration of ShapeMetriX and DIPS for geotechnical assessments. My name is Grace Wang, and I'm a geomechanics product manager at Rocscience, and I'll be moderating this session today. So it is my pleasure to introduce our speakers. First, we have Dr. Markus Pötsch, who is a technical specialist from 3GSM. And here with me is also my colleague, Yalin Dogan, who is an application engineer with Rocscience. And they will be working together to show you how to go from geological mapping in ShapeMetriX to joint orientation analysis and kinematic assessments in DIPS. So first, some background on each company. Rocscience provides innovative 2D and 3D software for the civil, mining, and geotechnical sectors. And over the past 25 years, it has grown from a team of 4 to the team of 80 that is today. Currently, Rocscience offers a total of 19 software, and you can see in this ecosystem map that most of these software are interoperable to meet your various design and analysis needs. Now, we also understand that numerical analysis and design is only one part of the geotechnical workflow, and obtaining field data is a very large part of geotechnical engineering. So for this reason, Rocscience would like to provide integrated software solutions that can carry you from geological mapping and characterization all the way to geotechnical stability and hazard assessment. Which is why here we have 3GSM, which is a company that specializes in providing 3D software for geological mapping and survey. And the specific software from 3GSM, Dr. Markus is going to show today, is ShapeMetriX. And this is a very powerful package with 3D visualization for geological mapping. So ShapeMetriX is the first item on the agenda today, and this will be followed by a Q&A break for any questions you might have about ShapeMetriX. Then we will have a DIPS presentation by Yalin and an integration example by both Markus and Yalin. Now, throughout the presentation, please feel free to type your questions in the chat section, and we will try to address most of your questions during the Q&A session. And if we don't get to them today, don't worry, we'll follow up with an email with all the answers within 2 weeks of this webinar. So without further ado, let's turn to Markus.
Thank you, Grace, for this nice introduction. Good morning, good afternoon, and even good evening in all parts of the world. I hope we can bring an interesting information and webinar for you. So what I want to do is to introduce a little bit on ShapeMetriX, what it basically is. ShapeMetriX is a 3D imaging system designed for geological mapping and geotechnical assessments. It, in particular, does not only the assessment, but takes pictures from cameras, processes those pictures into a 3D model, and allows for geotechnical assessment then. Here at the first part, the pictures can be taken originally with handheld cameras, DSLR cameras, which have been applied from the floor to survey the rock faces. Nowadays, a more favorite application is, of course, the use of drones, which carry cameras, and they can generate comprehensive views on the rock faces in rock slope, in open pits and quarries. So these are quite favorable, applicable. As I mentioned, terrestrial application also works underground if you put your camera on a tripod. Then if you have your pictures, you go to the next step. You load the pictures into the 3D model generator, which we call multiphoto in ShapeMetriX. This is an automatic and versatile process, and it generates accurate 3D models and supports several ways of referencing. And once you have gone through the model generation process, you go into the geological mapping tool, which is the analyst. And this tool allows you to define traces and areas of daylighting joints, to measure in joint orientations, determine joint sets, make some stereo net analysis, and determine certain kinds of statistics. Today is also a special day because for the first time we want to introduce a new feature which is related to Rocscience DIP software. We have generated a dedicated export interface to the DIP software. So stay tuned for that. And the other thing I want to mention here, which is also important for the user, this is an integrated workflow from the picture until the 3D assessment or the geological mapping. If you as a user would say, what should I do if I already have data? In the next major of the software, we will provide a interface for importing already existing 3D data based on textured surfaces and even lighter point clouds. So this is I wanted to show on a slide. Please let me directly show everything I've mentioned here in terms of the presentation in the software directly. So let's start with the pictures first. So we have pictures, and I have an example here which is from a drone. So we see here pictures taken by drone. We see here looking vertically downwards, so-called nadir photos, where we see the top of bench and the floor, and we see just in the middle the face, the bench face. We realize instantly that the face is not very prominent in the picture, and this is nothing what a geotechnical engineer or a geologist will be happy with. So what's also necessary is to have a more favorable view onto the face to get more details, to have it more prominent in the picture and have more parts of the face captured in the 3D model. So it's important not just nadir. Surveying many times just generates nadir photos, but for geological and assessment, we want to have a frontal view to the face, independent of what the face orientation would look like. You see here, the drone pictures, they overlap, like kind of 80% overlap between adjacent photos, and this is necessary in order to generate the 3D model accurately and fully automatically. So we have that set of photos. Let's jump over in the software. So I'm going here into the multi-photo. You load the pictures into the software. I prepared it already for you. So this is a bunch of photos, a rather small project, like 72 pictures. What you do is you give it a name, and then you press the Start Reconstruction button, and this will, in the ideal case, guide you from the start all through the processing till the end of the process until the final 3D model. And there is possibilities to jump in during the reconstruction, but this is not a mandatory task. So you can take with you, this is a fully automatic process from start to the end. Let me show you how such an example might look like. This is a 3D model from that set of photos I just shown you, a bench example. We see the detailed geometry already. And what I want to show here is also the set of cameras. You see these green pyramids. These cameras are the positions at the time when the drone took the photo, reconstructed from the pictures. And we see here one track looking vertically downwards, this one here. And there is another one overlapping here. And we see here on the right-hand side, we see here the frontal photos towards the face. And here at this track, we have also an intermediate camera view in order to get around the corner from 90 degrees up to frontal to the face. So This is a typical setup at the bench. So flying back and forth, nadir, inclining the camera like 30 degrees and then incline it to 60 degrees. Okay, there are, at the end, you have to register the model. This can be done with control points or with GPS on the drone, but I don't want to go into too much detail here. Then, once you have done that, once you have generated the 3D model, we jump into the assessment tool. This is the analyst software in ShapeMetriX, and this allows us for a thorough inspection. We can look at it from front, from the back, and zoom in here or zoom out, get the comprehensive view of the entire face. And what you can do here with these tools here on the right-hand side, you can map the identifiable discontinuities, joints, fault zones, zones of weaknesses in general. So let me show that how that might work. So I'm going here into the area tool and identify a couple of patches. Let me explain that feature later on to you. So we have here those areas. And then we can have here traces. Traces are linear elements. Areas are more like closed polygons. And let me map those traces here. Over here, and over here, and maybe that one over here. And then I can go here in the clustering function and see how they fit together and get already 2 joint sets identified. So this is a quick assessment of the features. So I used here the area. We have 2 areas, the region grow and the interactive area. The region grow, that one aims to find the planar area around a seed point, a click point, and looks around the whole 3D model where could be these planar areas, and you can always extend. And then it identifies the points of the 3D model, calculates the area. We see all the measurements here in that structure list on the right-hand side. And you see also that arrow here emerging from the area. This is the average orientation of that patch, represented as the normal vector of that measurement. So we get here the size of the area and the dip direction and the dip angle of that patch. And this is, of course, then available for all of the measurement you have identified. You might have seen the normal vector shows the tail, and on the other hand, here it shows the spike. So what does that mean? If we see the tail, we are facing an overhang. And if we see the spike, we are facing a joint which is dipping towards the observer. So let's jump over here to the traces. The trace is used to identify linear features, which are quite common in Rocscience characterization. And what you do here is you click a start point and you click an end point, and it's supposed to find the connection between start and end point automatically based on the texture information, on the color, on the contrast between start and end point. So it's not a straight line, but it follows to a certain degree the irregularities indicated by the texture. And also that trace here has this, it looks like a triangle. Actually, it's a kind of a square. And that one is also an orientation cursor indicating that there is available the orientation also for the trace. And that works because usually in rock masses, the traces, they are not perfectly straight lines. They have some irregularities. And assuming that a joint is at least at a certain extension, a plane, this is a plane is fitted to it, to that irregular trace, and an orientation provided also for the user in terms of, again, dip direction, dip angle. So here we see it's not the normal vector, but it's the plane itself, what we see, the plane of the joint forming the trace on the surface. That was the guided trace. For both of the trace and the areas, we have interactive features, interactive modes. Let me jump over here, this one. So, okay, this was not the right one, but doesn't matter. So the interactive area, you just click the area and you get the average orientation and the size. And we see with this big area here, you would assume that it identifies the entire patch as a joint, but this is a clear indication that this is already a wavy, irregular joint. So we describe that with a couple of individual measurements. All those measurements can also be edited from the context menu. You can move, delete, abandon your points, insert points. So you get access to all of these measurements and can modify that so they are individual structures within the 3D model. And then you have seen the clustering. Everything can be grouped automatically based on the similarity in the orientations. So we can identify structure sets, but the user is also able to define single individual structure sets by himself or by herself. So let me jump over here to the same phase, but through a more elaborate example here. So we see here already quite a comprehensive assessment with lots of areas and even traces. We have a couple of joint sets identified, and we can have a look at the stereographic projection, the StereoNet. We see here the green areas, so the dark and the light green, which are dipping in that direction. Then we have the blue ones and the red ones, which are forming these highly persistent joints over here. And we can get for all of the measurements, we can get statistics. So the average orientation of that set in terms of dip direction, of dip angle, center of gravity. Then spherical aperture, which is a kind of spherical standard deviation, where we see this as a dashed cone around the mean. This is the spherical aperture. And then we have the Fisher's concentration, the degree of orientation from 0 to 100%, and the cone of confidence, which indicates the confidence that the mean will reside within that cone. So this is the dashed cones around the mean. So this gives you an indication about the spread of the joint set and how well the mean is defined within that set. Okay, then we have other analysis tools as well. So we can go to the trace map analysis. Let me switch over to this one here and turn off the intersection mark. So this is related to the red set. So how does this come to be? So the software automatically takes the measurements of the set. Can be the entire set, or for the advanced users can also be subsets of one set from a different observation, different phases. And it takes first the mean orientation of that set, which is one vector, and the dominant extension of the traces, which is another vector. And from these two vectors, it generates a kind of projection plane, which we see here as this prominent rectangle passing through that 3D model. And then we can project all of the measurement of the red set onto this projection plane. And this is the sketch what we get. So this is a little bit stretched here, but if I zoom in here, we get the projected traces. So that one here. And we get the dashed lines are the distances between the traces measured in direction of the mean orientation of that set. So this is a quasi-true spacing for non-parallel measurements within one joint set. So something what we frequently encounter in rock masses. So we get the measurements here. We get information on the traces. Let me put that more here. Then we get also the mean for spacing and trace length and the statistics. And the software also samples the measurements on the spacing in a cumulative distribution with a histogram, both for the spacing and the trace length. And this is available for all of the sets, of course. So we see the distribution for the different sets. Okay. Then I hided one measurement from you. Just let me jump back here. This is the single orientation measurement. That's the most original one. That's the compass, the geological compass. And if I zoom in here, maybe this is quite intuitive. We see that normal vector indicating the orientation, and then we can walk with that measurement across the 3D model, and we see how it adjusts according to the surface. So this is the more intuitive for users of the geological compass. Another feature which is interesting for geological modelers and for geomechanics engineers. So you can select all of the measurements or one, and then you can use that, what we call the discontinuity feature, the discontinuity model. So here on the map, this is observations, this is measurements on the surface, and sometimes or many times you're interested how that would propagate or project into the rock mass, and therefore you can add a discontinuity model, and that model can be can have different shapes, an ellipse, a rectangle, or let me stay at the circle here. We can adjust the size. Let's do 20 meters, and then we can unlock it from the original measurement, and we can adjust the orientation in terms of with the purpose of modeling, or we can also move that discontinuity plane to a more favorable position down here, and then we see how that might project into the rock mass. If you're applying that several times for the prominent features, what you can do is you can highlight the rock structure in terms of a modeled discontinuity set, what we see here for the red set, and get an impression, a more abstract impression of what the rock mass is all about. So from sensing the pixels, generating the 3D model, mapping the structures as you would see it on the surface, and then get an abstraction of a rock mass model for the further analysis for a geological model or a geomechanics analysis. The important thing here for these discontinuity models is that you can export those models. So they can be exported directly from the software here as a DXF polygon or as a DXF mesh. And so you can directly use those as zone of weaknesses in the rock science or geomechanics analysis tools like RS3, Slide 3, or even Rockslope. Okay, this was all benches. The whole thing is not only applicable for benches, but it works also for on scale for open pit. This is just a matter of the amount of pictures to process. This can result in really large projects, which give you a comprehensive view. And if you want to maintain a certain resolution, then you have also quite a lot of pictures with high resolution and can zoom into the model and identify also small features and structures on the model. That one is more used to identify prominent structures in the pit, as we see those down here. For instance, we could map those structures down here, like with that trace tool, and get the dip direction and dip angle of that feature. So just to let you know, benches can be analyzed in very high detail, but it's also applicable for larger scale operations, open pits and slopes in mountainous regions. So if you're keen now to try that one, I want to give you some advice how to download or how to get the demo version. You have seen probably in the introductory slide, there is a link. This will be provided to you. And with that link, you will get directly to 3GSM's webpage at 3gsm.at. And here you can register yourself for the demo version. And if we receive that advice from you, then we will send you the demo version. Anytime, so if you don't have that link, you can anytime go to 3gsm.at, go to the support region and request your demo software in the topic demo software, and just inquiry through that form. Then you are entitled to receive the demo version. Let me get back to the analysis. So once you're happy, and this also brings me to the end of the presentation from my side. If you're happy with your assessment, if you're ready with your assessment, you can save it, you can further process. But the most important feature today is to export the measurements directly to DIPS. And you find that here in the export section, right on top, export to DIPS, which is a file which you can seamlessly open in the DIPS software, which Yalin will show us in just a few seconds. That's from my side. Thank you for your attention.
Now let's turn to Yalin for the presentation on DIPS and the integration exam.
Hello all joining us today in this webinar, and thank you, Markus, for your very interesting and informative presentation about ShapeMetriX. Now let's move on to DIPS and have a brief introduction in DIPS and how it utilizes in kinematic analysis. So DIPS is a stereographic projection analysis program designed for interactive analysis of orientation-based data, the visualization of orientation vectors, density contours, planes, intersections, and traverses. In DIPS, you can perform kinematic analysis of the joints using the orientation data taken from the field in order to determine if the slope you're analyzing is susceptible to planar or wedge type of failure or toppling. And DIPS also allows users to perform true and apparent spacing in joint set rock quality designation analysis, RQD, and frequency analysis on the field data. Additionally, you can view the strike density, frequency of your measured data using the rosette plot, which is included in DIPS. You can also draw user-defined planes, sets, and include annotated tools for your reporting purposes. So the stratigraphic projection allows the three-dimensional orientation data to be represented and analyzed in 2 dimensions. Stratigraphic projections remove 1 dimension from consideration so that the lines or points can represent planes and the points can represent lines. Once the stratigraphic projections are completed, you can then identify critical zones, vectors, and intersections on a StereoNet overlay with the kinematic analysis of planar and wedge sliding or direct and flexural toppling failure modes. You will then also have the option to export kinematic analysis results to a spreadsheet program containing critical vectors, intersections for all failure modes. DIPS also includes 3 built-in analysis options, as I have mentioned. Joint spacing to calculate the true and apparent spacing between joint within a set, and RQD analysis for assessing rock quality designation, and joint frequency for counting the occurrence of joints along each 1D distance interval on a linear or four-hole traverse. So the stability of rock slopes is often significantly influenced by the structural geology of the rock. The structural geology refers to naturally occurring breaks in the rock, such as bedding planes, joints, and faults, which are generally termed as discontinuities. The significance of discontinuities is that they are the planes of weaknesses in much stronger intact rock. So the failure tends to occur preferentially along these surfaces. Therefore, the discontinuities may directly influence the stability. And almost all rock slope stability studies should address the structural geology of the site, and such studies usually have or involve 2 steps. First one is to determine the properties of discontinuities, which involves mapping outcrops and existing cuts, if any, as Markus showed us a few minutes ago, and examining diamond drill cores. And the second part is to determine the influence of the discontinuities on stability, which involves studying the relationship between the orientation of the discontinuity and the face. The objective of this study, which is termed kinematic analysis, is to identify possible modes of slope failure. Using one of the most used and beneficial features of DIPS, users can perform kinematic analysis of the joints using the orientation data. And please note that kinematic analysis is a preliminary analysis that allows you to easily and quickly check for various rock slope stability failure modes on a StereoNet plot, and which is to be followed by a detailed stability analysis of these blocks. So without further ado, and let's jump onto our example. We have 2 examples today. The first one is for utilizing DIPS and kinematic analysis. So we'll find what is the likelihood of planar and or wedge instability. And the second one will be about the integration between ShapeMetriX and DIPS. So let's start with open a new blank DIPS file. What I'm going to do today is I will import an already measured data from the field. But first, let me define a traverse which those measurements are taken from. It is a planar traverse, which I will ID as 1, and the orientation of this planar traverse is 45 to 135 degrees. So once I define the traverse, you can see it's interactively, the grid data interactively now has the traverse column. And next, I'm going to go and import my field data. To do so, I'll just use the DIPS import wizard option, and grid data information will be imported. So here is my spreadsheet file with the data taken from the field. I have 6 columns. The first one is for dip angles. The second one is for dip directions. Third column is for the traverse, which the measurements are taken from. Fourth column will be for spacing. The fifth one will be length of the discontinuity. And the last one, the sixth one, will be the type of the discontinuity, whether it's a joint, a bedding plane, or a shear plane. So we have 3 columns over here on the grid data, and then I will add 3 more. As I have mentioned, the fourth one will be spacing in meters. The fifth one will be length in meters, and the last one will be the type of the discontinuity. So let's assign these columns in the spreadsheet file in this data dialog box. So orient 1 is column A, the dip angle of our measured data. B is dip direction. Traverse is C. Okay. Let's define spacing with column D, length, column A, and type of the discontinuity will be column F. Next, I just finished importing my data using the spreadsheet file, and I can move on to contour preset to see the density contours of my measured data. So let me open the pole vector display. You can see the poles of each field measurement, as well as let me change the projection to equal area. We can see the density contours as well as the pole vectors. What I want to do next is I'd like to add sets using the add set window. So the measurements or discontinuities having poles falling in this set is compiled as one set, so I can proceed with set versus set analysis later. Let's define a second set over here. Okay, a third one. And a fourth and final one over here. So these are all my sets, and I'm ready to move on with kinematic analysis and set versus set analysis in wedge sliding checks. So under analysis options, kinematic analysis, and let me enable the display kinematic analysis option. And this drop-down menu gives us the option to define the failure mode. Let's proceed with the planar sliding. And the slope dip for this example will be 59, and the slope dip direction will be 220. the friction angle and lateral limits will stay the same. Let's highlight the critical vectors. You can see our StereoNet plot is interactively changing, but when I click OK, you can see the red dots here, which refers to the poles of discontinuities which might have or critical for planar sliding. So out of 303 total measurements, 18 of them, or almost 6% of them, are critical or might subject to planar sliding kinematically. So these measurements might need a further planar sliding check. And let's move on to wedge sliding kinematic analysis. When I just switch to wedge sliding, you can see interactively my critical zones are changed. And you can see the now highlighted the intersections of all the possible intersections that can be formed by 303 field measurements. So this includes all the grid datas. But what I'd like to do is I'd like to conduct a set versus set wedge sliding analysis, which means only the selected sets can form a wedge. So my set A or set 1 will be the one I defined as ID1, and let's select the set B as set 3. So in that case, we're having a set versus set wedge sliding analysis, which is only conducted considering the possible intersections of set 1 and set 3. And one last thing I would like to show you is, within this example, is the kinematic sensitivity. So under the kinematic sensitivity option, let's define a range for slope dip from 49 to 69 with 1 degrees interval, and with slope dip direction, let's define a range between 310 to 330. And when we click OK, you can see how our critical percentage or critical count of intersections are changing with various or variable slope dip degrees and dip directions. You can follow the dip direction from 310 to 330 does not have a significant effect, while our dip angle of this particular slope has a significant effect on our critical count or percentage in terms of wedge sliding. So this kinematic sensitivity option gives you a chance to make a reliability-based analysis. So this was the first example, and let's move on to the second example. Let me open a new DIPS file and close these ones. Okay, a fresh DIPS file. The latest build of DIPS now has the ShapeMetriX direct import from ShapeMetriX option. So by clicking on this button here, I can directly open a ShapeMetriX file exported from ShapeMetriX. So here is my file with all dip and dip direction measurements, as well as the locations of these measurements in XYZ and the persistence values. So everything is imported in DIPS within a second. Then I'll follow the same steps, go to the contour preset, enable the pole vector displays, and change my projection to equal area. Again, I would like to define sets, but now with freehand drawing. Okay, this one, very roughly.
Okay.
This will be my set 1. Okay, another set over here. And we'd like to add one more set for the poles over here. Okay. Now we have our 3 sets defined. Just would like to basically show you our dynamic filter option. By clicking on that button, you can define a filter and filter out the certain measurements in your file. So let's name it as dip. So I will just define a dip filter with having more than 20 degrees and below 32 degrees, or the ones having more than 50 degrees or angles of dip and less than 75. Okay. Now we're good to go. We defined our dynamic filter, and using this toggle down menu, just when we change our unfiltered data option to dip filter, you can see only the measurements that satisfy our filter is now included, and the others are filtered out. And this is how you can dynamically add a filter. Let's go back to unfiltered data and conduct a kinematic analysis, another wedge sliding analysis. This time our slope dip will be 50, slope dip direction will be 55, and the friction angle of this kinematic analysis will be 25. And I will once again go with set versus set intersection type. So my first set, or set A, will be defined the ones that I defined with set 2, and set B will be the one that I defined as set 3. Okay, you can see the critical intersections of set 1 and set 2 and set 3, which almost 80% of intersections are critical in terms of wedge sliding. So we can have a further check with S-wedge. So this is an integration between dips and S-wedge, which we started with ShapeMetriX, obtain the dip and dip directions, the locations of our discontinuities. Then, thanks to the integration with dips, we conducted a wedge sliding kinematic analysis. And now we're moving further to S-wedge, which allows us to conduct wedge stability, further wedge stability analysis, including the external forces. So our dip was 50 degrees, slope dip and slope dip direction was 55, and the slope dip direction of the upper face will use the slope dip direction. And with the import from dips button, we can now import the joints from dips, joint sets, which we defined in dips. So our first joint in S-wedge will be the joint set 2. And our second joint in SWedge will be the joint set 3 in DIPS file that we just performed the wedge sliding analysis. And within minutes, you can go to SWedge and conduct further wedge stability analysis using all the ShapeMetriX, DIPS, and SWedge integrations. And further integrations of Rocscience's other programs with ShapeMetriX are also on the way. And before wrapping up the webinar, I would like to show you a teaser screenshot from a rock slope tree analysis. So this analysis is conducted by using the ShapeMetriX to obtain the geometry and structural mapping data and rock slope tree to perform the block stability analysis. So stay tuned for our next webinar on rock slope tree and ShapeMetriX integration, and follow us on our social media for the webinar announcements. And thank you today for joining us.